Okay, right. So good afternoon again. We're going to pick up from where we left off yesterday, and we're talking about implementing binary search trees in the hope. What we saw yesterday is that the performance for inserting, deleting, searching binary search tree was basically order the height. So that by itself is success, because the very last thing we're discussing is that you could have variable structures on your binary search tree, in that it's possible for you to have inserted elements in ascending order or in descending order, or some other order that then causes the tree to not look so nice. What do I mean by nice? That what we call, it's not balanced. Right. Somebody was giving me interference on the line here. Right. So what we call not nice is that basically the tree is not balanced. And of course, that is entirely up to the user, because the user decides what values are being inserted. And if the structure of your tree, and therefore your performance, is going to depend on the user's choice of what order to put elements in, you're going to suffer, the performance of your algorithm suffers on that basis. And what we want to do is try and mitigate against that. We don't want to have to depend on the user being friendly to our system for it to have good performance, because then that's really just hoping for best case scenarios. Right? So remember that the point was yesterday that the structure of a BST depends on the order in which elements are inserted. So remember that before that, what we did was we proved that the time for insertion was equal to the time for deletion, which is basically equal to the time for search or lookup, which was big O H. In other words, at worst, the height of the tree. Unfortunately, though, and coupling these two observations together, because the structure depends on the order in which elements are inserted, it means that, so it's possible to have what's called a degenerate tree. For example, a tree that looks like this. And basically in that case, we have our height is actually all the nodes, it's n nodes. In that case, the performance, because it's order H, is essentially order n. And that's no better than a linked list. Right? We would like a picture that looks more like something like this, where you pretty much have every level as full as possible. Not necessarily everyone exactly full, but a tree that looks closer to this picture is going to have H being, what's the relationship here between H and N in this? Very good. It's going to be proportional to the log, or in the order of the log of the number of nodes. Now, if we have the second scenario, then it means that the performance for all these operations is great. Because remember that log n is much faster than n, right? Remember, just think your hacker-rank problems. If your input size is 10 to the 8, order n is too slow, but log n is no problem, right? So we want a tree that looks closer to this picture than to the first one. We don't want a degenerate case. We would love for our tree to look like this. Unfortunately, because it depends on how the user uses it, we can't always guarantee this, at least not in terms of the way we've described binary search trees so far. So what's the fix? What we want is self-balancing binary search trees. Okay? So self-balancing binary search trees will aim to construct a tree that the difference between the longest path lengths between roots to any leaf won't be too large. Okay? Another way to put it is that if we could somehow guarantee that at every level, the difference in heights between the two sides isn't too much, then that would also lead to balance, something closer to this. Okay? So a self-balancing binary search tree that's what a self-balancing binary search tree is going to achieve. So because of this order of growth relation, it's not tight, not necessarily exact. Now there are some structures that do actually provide some kind of guarantee that's much tighter than this. So we're actually only going to study one specific method for implementing a self-balancing binary search tree, and that's the red-black tree. So before I jump into that in great detail, I just want to make sure that you're not under the false impression that that's the only thing that's available. But in a way, it's the more modern method. So an example. There's one called an ABL tree, and the A, B, and L stand for the people who invented it. I don't remember all their names, so I'm not going to try tell you who. ABL trees. In this case, what these will do is guarantee that the difference in height of the left and right subtrees at any node is at most 1. Okay, of course, if you can achieve that, if you can guarantee that, you can see how everything will be balanced. And then, of course, the second one, and this, our red-black tree, are a kind of improvement on the ABL tree. But these are not, well, I won't say what they are yet, but since we're going to go into great detail on what they are and how they work, I won't give you the summary. But they also provide a certain level of balance, but in this case, it won't be as tight as differing only by at most 1. Right? So, okay, so before I get into the details of what a red-black tree is and tell you all about that, just as a quick exercise to ensure that we're all on the same page, I'm going to draw some tree structures and you tell me which ones are balanced. So I'm drawing all the nodes now. These are two separate trees. Is the one on the left balanced? Okay, fine. The people at the front are laughing at my questions and saying, what are you doing? Neither of them is balanced. Move on. Okay, so is that the sentiment of the class? What, did I just insult your intelligence? I apologize. All right, yeah, neither of these is balanced. Okay, so don't be fooled. Just because it looks okay from the top on this side doesn't mean it counts as balanced, because you need that balance to appear at every level. Okay, that sense of balance. So for example, this node will be very unhappy because the difference in heights between this left and right side is huge compared to the height of the overall tree. All right, so let's get into this red-black tree and look at specifically what it is. All right, so from here on, I'm going to write RB to stand for a red-black tree. So first of all, it's a binary search tree, but it has some extra properties. You know, it's unfortunate that this is the room that we have to introduce this in, because the board is tiny and I have a lot of stuff to draw and write. So basically there are 4 other properties in addition to being a binary search tree. So remember, it's already a binary search tree, so it already has the ordering, the left to right ordering that we have for all binary search trees. And it's already a binary tree because it's a binary search tree. In addition to that, first of all, every node is one of 2 colors, red or black. Second is that the root is always black. The third one is a red node may never have a red child. And the fourth one is perhaps the most technical of them, at least to describe in the first instance. And this is, there are a number of alternative equivalent ways to say this, but I'll start with the one that perhaps is easiest to picture. And that is that if you were to count the total number of black nodes on any path from root to a leaf, you'll get the same number. Okay? So let me just try to capture that. I hope I can have a space down here to give you the name of that. That number is called a black path length. All right, so the number of black nodes on any path from root to a leaf is the same. It's the same regardless of which leaf you choose. This number is called the black height of the tree. Okay, so it turns out, any questions on that? All right, it turns out that, yes, go ahead. No, it does not. So black nodes can have black children, red nodes can't have red children. All right. So, okay, on that note, it's the combination of the 3 and the 4. And we're gonna do a little, I won't do a full proof in class, but I'm gonna leave one for you to do in tutorial. I'll discuss one side in lecture. But it's a combination of properties 3 and 4 that's gonna try and establish that balance. Because property 4 is saying number of black nodes, basically the black height is the same. So that's a form of this, rough it off already. That's a form of that balanced picture. The difference though is that it's only among the black nodes that will have that balance. So you're going to be allowed to intersperse red nodes in between the black nodes. But if red nodes can't have red children, you can't put too many red nodes on any path. That make sense? All right. So that's this trick. That's how it works. All right. Now, let me write down some properties, and from those properties, you're going to see how this all kind of comes together. And some of these you'll get to explore in the tutorial for next week. But the critical ones, which give us the properties that we want to exploit, are the ones I want to bring out. And then we can talk about how we actually maintain a structure like this. So it's one thing, before I jump into the properties, it's one thing to say, okay, if I could maintain these properties, look at all the wonderful things that would happen. It's another to show how you actually achieve those, right? So we have 2 tasks ahead of us. One is, why is this a good idea? And the second is, now that we've shown that it's a good idea, how do we actually do it, right? So we do that one at a time. And you notice I drew a line here. We may not actually get to how we do it in today's lecture. We'll do it next week, Monday, because there's no class on Friday. All right. So here we go. Let's, for a given red-black tree, let n be its number of nodes, let k be its black height, and let h be its height. Okay? Now what we want to do is try and establish some relationships between these. So let me start simple. Let's see if you can establish a relationship between the black height and the height. Can you put any bounds on if you know the black height, can you put any bounds on the height? Height has to be at least, wait, what? What is greater than equal to? Height is greater than equal to the black height. Good. So you know for sure that must be true. Why is that obvious? The black height is the number of black nodes. The height is the total number of nodes. So that total number of nodes can be less than the number of black nodes. All right. Okay. Can you put an upper bound on the height? Very good. Height is at most 2 times the black height. Why is that? Because you could have alternatives. For every black, you could have a red. Why can't I have more? Red nodes can't have red children. So you'll never, if you're looking at a sequence from root down to a leaf, you will never ever encounter red, red. You could see black, red, or you could see black, black, black. You know, you're black, red, black, black. But you can never see black, red, 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 because red nodes can't have red children. So every time you see a red, you're guaranteed to see a black next. And therefore, if you know what the black height is, which is k, then that means I already have k black nodes laid out. And if I'm trying to maximize that path length, I'm going to stuff as many red nodes as I can I can't stick two consecutive red nodes in that path. So that means that the best I could do to maximize that length, which is what I'm trying to do, trying to get the upper bound on H, I would have to basically stick a red node in between, basically after each black. Make sense? So at worst, for every black node, there could be a red node, which would then send the height up to 2 times the black height. That make sense? Great. All right, so that's one important property. Second one. Now this one is not something that you could reason out just by knowing these properties, but we can prove it. We'll talk about how to prove it. Let me write it down first. This one is going to relate the black height to the number of nodes. All right? Now it turns out that n must be at least 2 to the k minus 1. And it can't be more than 4 to the k minus 1. Now I'm going to show you why one side of that is true, and I'm going to leave the other side for you to do in tutorial. You know why it's already? First side makes sense? Why does the left side make sense? You don't see it yet, but you feel it. But the second, the right side, you don't feel it. Well, then maybe I will give you the proof for the left side, since you feel that one. And then you can work out in the tutorial the proof for the right side. All right. So here's how we're going to do this. It's a proof by induction. And I'm going to take this opportunity. I know that you would have done proof by induction probably in maybe 6th form, and then maybe in the discrete maths course, maybe in COMP2211. All right. But what I'm not so sure of is, did you ever do induction, a proof by induction on anything other than a formula? Did you ever do proof by induction? Okay. Did you ever do a proof by induction on a discrete structure, like a tree or a graph? Right. So this is one opportunity to do that, for you to see how you do it. So I'm going to walk you through that then. All right. So let's say we're trying to prove the left-hand side. We can prove that by induction. So we'll do only one side. We want to prove that 2 to the k minus 1 is less than or equal to n. And I'm just going to sketch the proof here because the details are important, but it's really for you to practice. So of course, you know how proof by induction works. You have 2 parts, right? You have the base case that you have to establish separately, and then the inductive step is what that's called. The inductive step itself requires you to define an inductive hypothesis, which maybe here they may have said, assume it's true up to a point. That's what's called the inductive hypothesis. And then based on the inductive hypothesis, you're going to make an inference that it holds for the next point. Right. Now the challenge for something that's not a number, I mean, yes, these are numbers, but I'm reasoning about a structure, a data structure, something that is a tree. So you have to first, before you jump into the induction, you have to ask yourself, what is the induction on? What variable am I going to run my induction on? Obviously, it's going to be some kind of discrete variable, but everything there is discrete. So when you look at this, you might think, well, I have n. I could contemplate running it on n. Then in that case, I'm going to have to reason about a tree that has n nodes. How is it related to a tree that has fewer than n nodes? And the problem with that is that just knowing the number of nodes doesn't tell me anything about the balance. So maybe that one is a little hard. How about the black height? Maybe I could try and reason about the black height. Can I make a relationship between a tree that has a black height of k and a tree that has a black height of k minus 1? Can you think of a relationship that I could say? In other words, if I have some inductive hypothesis about all red-black trees whose black height doesn't exceed a number, and then so I assume that's true, and now I want to reason about a red-black tree whose black height is actually at that number, I'm gonna have to use something other than k, m or something like that. Can you imagine how I might envision a substructure of my tree of black height m that involves subtrees of black heights less than m in a useful way? No? All right, let's try. But that's what we're gonna do. We're gonna run the induction on the black height. All right, so base case, what do you think would be the smallest black height that we would care to think about? Yeah, 1. It turns out it would work if you tried 0, but 1 is a reasonable base case. Now in that case, if you have only, oh, by the way, by convention, I'm gonna draw, I should have mentioned that before, because I'm using one color ink. When I'm drawing, you will too when you're doing your test and your exam, we're gonna draw different shapes for the red and the black nodes. So I'm gonna draw the black nodes as rectangles and circles for the red nodes. Okay? So if I have a black height of 1, and what I want to do is now ask yourself, what is the smallest red-black tree that you could draw that has a black height of 1 node? That's it, right? After this, I would just have 2 empties. So that's the smallest tree. And in this case, how many nodes does it have?
1.
And so in fact, what this was saying is that it shouldn't be that 2 to the 1 minus 1, which is equal to 2 minus 1, which is equal to 1. This was not supposed to exceed n, which in fact is true. So we just established a base case. Now for the inductive step, we need to identify the inductive hypothesis. What do you think would be a useful inductive hypothesis here? For some fixed value m, what are we going to assume is true? That's what I said, yeah. That what? For all black heights less than m, that the proposition was true. Yes? So what one says, so for some fixed m, the only thing here that's fixed is the m. What we still want to say is that for all k that are strictly less than m, the thing we're trying to prove is true. Maybe I might need a little slightly wider column. It's okay. Okay, so if that's true, now what I want to ask about is what's the smallest red-black tree that we could construct that has a black height actually equal to m? And how does that look relative to other red-black trees that would satisfy our inductive hypothesis? Now the smallest looks like what? Okay, so I have the root being black. Both are black. So, but I now need to think about not just the children, I need to think about the subtrees. So I'm gonna have, yeah, because I'm trying to make it the smallest, I'm gonna emphasize that the child is black, but I want to focus on the subtree underneath it. That is as small as I could make it, yes? That has two subtrees. How could I have made it bigger? Like I could have put in a red node here and I made the red have two subtrees. That would have made it a bigger tree. But we're trying to minimize the number of nodes here. We're trying to prove this side. So I'm trying to contemplate what is the smallest possible tree given that the black height is k. All right. So now in our case, for where we're trying to extend the inductive hypothesis, the black height is m. Remember what black height is total number of black nodes from roots to any leaf. So if the black height is m here, what can I say about the black heights of these two subtrees? M minus 1. Yes? Ind stands for inductive hypothesis. Okay, so now I need to talk about the total number of nodes in this tree. All right, so let me call this side NL and this side NR. If my total number of nodes is n, I could write that n is equal to NL plus NR plus 1 for that root. Now, do we have a minimum, a lower bound for NL and NR? By the inductive hypothesis, we do, because it says once the black height is smaller than m, black height is actually m minus 1, which is smaller than m, then we can invoke this presumption. Yes, this is the hypothesis. So in other words, we know that NL is at least 2 to the minus 1 then, minus 1. So this is at least 2 to the m minus 1 minus 1. That's for NL. Plus for NR, it's the same thing. It's at least 2 to the m minus 1 minus 1. And then we had a plus 1. And when you add these, 2 to the m minus 1 plus 2 to the m minus 1 is 2 times that number, which is 2 to the m. That's 2 to the m minus 2 plus 1, which is 2 to the m minus 1, which satisfies what the inductive hypothesis would have said had we extended it to m, which therefore means that the whole thing is true. Yes? So now you just saw how to run a proof by induction on a discrete structure. You have to identify what the inductive variable is, and then you can run it like you normally would for your typical formula or whatever else you've seen it on before. The key thing is you have to reason about how the structure at one size depends on the substructures at some smaller size. Okay, that's where it gets different. All right. Now the reason for showing you this was not to take you on an excursion through how to do a proof by induction, but rather to actually get to how we're going to make the self-balancing property work for us. So what I'm really trying to do is establish for you that in fact this is going to be a benefit. Let's examine what this property, the second pair of properties, tells us. Notice that I have on one side 2 to the k minus 1. So now we're back to talking about in general black height to k at most n, which is no bigger than 4 to the k minus 1. I could add plus 1 to all three sides. Yeah. And so that gives me that 2 to the k is at most n plus 1. which is at most 4 to the k. Now, if I take the log, why is it legal to take the log? Because base 2, that's, I mean, the question I'm asking is, why is it legitimate to take the log and preserve that inequality? Because log is an increasing function. All right? And yeah, because log is an increasing, let's leave it at that. Log is an increasing function. So if I take log, then that means that k, because the log of 2 to the k base 2 is less or equal to the log base 2 of n plus 1, which is less or equal to the log of 4 to the k, which is going to be what? Why is it 2k? Right. So 4 is 2 squared. So 4 to the k is 2 squared to the k, which is 2 to the 2k. And when you take the log of that, you get this, the power, which is 2k. So now, what did we just learn here? All right, great. So the bottom line is that h is going to be on the order of log n plus 1. It's not equal, but it's going to be bounded. Now, I will leave the exact, excuse me. I will leave the exact nature of the inequality for you to derive in tutorial so you can mull it over. But as a consequence of this observation, this derivation, and the combination with property 1, we're going to be able to conclude that the height is theta log n plus 1, which a corollary. Oh, you don't know. A corollary is a statement that's true as a consequence of some previous theorems that you just finished proving to be true. But you don't usually elevate it to the status of theorem because usually a simple connection between it and what you've previously proved. Okay. So I hope that the point of all this was to show you that it's worthwhile investing some time into understanding how the red-black tree works. Because if we can manage to establish these properties, as a natural consequence of those properties, we will get the balance that we're seeking. Follow that? Remember that all the operations, the search, the insert, the delete, take time proportional to the height. And now we're going to be able to guarantee that the height will never be worse than log n. And so that will then give us that the operations insert, search, delete, all will operate in log n time. Got that? Yes? All right, fantastic. So, so at this point, we're now ready to start talking about how to actually implement this. So it's one thing, as I said before, it's one thing to say it would be nice if we could do this. It's quite another to make it happen. Before I can explain fully how we're going to make this happen, I have to illustrate a property of binary search trees for you. So there's an action that we can perform on a binary search tree called a rotation. And what a rotation is basically a structural rearrangement of a part of the tree in such a way that we respect the ordering property of the tree. Shouldn't really put it here today. All right, so there are two kinds of rotations. We can either rotate left or we can rotate right. Let's talk about what that looks like, what each of those looks like. It's actually a subtree. Okay, so this is an ordinary binary search tree now, and it's not necessarily a red-black tree. It could be any binary search tree. We can do this to it. I've drawn 3 nodes in the tree, and it doesn't have to be the root, it's anywhere inside the tree. And we have, so X is the value at the node I'm going to focus on, Y is to its left, Z is to the right, and these triangles represent the subtrees underneath each of those children. Now, if I rotate this left, how I want you to think about this is that I'm turning the link that goes to the right, I'm rotating that left. That's what you want to think about. So a left rotation about X is actually taking this link and turning it like that. Okay? So in other words, you're seeing Z as the right child of X. By the time we finish the rotation, to turn this link like so, Z is going to come up and take the place of X. So whatever X's parent was, that's now going to be Z's parent by the time we're finished. You mean animate the rotation? I'm about to draw the final picture. Oh, explain it again. All right. So we're trying to do a left rotation about X. What that really means is it's as if you took the link going to the right and rotated it left, keeping the endpoints the same. Which means that when I do this, the Z is going to go up and the X goes down. Okay? And so this link here that's holding on to the X is going to inherit the Z because this is going to rotate like so. What's going to happen to Z's children? We're going to discuss that. Let's talk about that. But it's easier to focus on one thing at a time. So if you get the connection of what we need to achieve, we can start there. And then once we start drawing the pieces, we realize somebody get left, and we'll find a place. Somebody got orphaned, and we need to find a home to adopt it. All right, so let's figure out how that's going to work. So let's do that rotation first. So this is a left rotation. So like I said, Z comes up, and X goes down to its left. Now imagine, since I moved X down like that, I don't need to worry about X's left side, do I? All that just moves with it. So therefore, Y is untouched, and Y's 2 subtrees are also untouched. Likewise, on the right side of Z, nothing really happened to affect it, so let's leave that alone. The right side of Z will still have its the children on the right side. So its right subtree will remain intact. Okay, so what was a casualty of this process here? Left subtree is Z. Now, we need a place to adopt this. Well, this looks like a natural place, but you can't just willy-nilly just drop the tree there because it looked like it could have put it there. What ordering property do you need to respect? Right, values on the left are smaller than the value at node, and those on the right are greater. So what we have to do is confirm for ourselves. We'd love to just take this tree and just put it here to the right of X. We have to confirm before we do that that actually is a valid move. Let's confirm why that might be okay. When we have ZL to the right of X, what does that mean? It's greater than X. So just by virtue of living on this side of the tree relative to X, we know already that all the values in ZL are larger than X. And therefore, it's legal to put it here. The second thing is it okay to put it left of Z though? Well, it used to be left of Z, so it must still be okay. So we had two conditions to check, and in fact, it's a valid thing to do. So in fact, that's exactly where we're going to put it. The question was, will the value at the node of ZL have to be greater than Y? And the answer is yes, because X was already bigger than Y, and everything in ZL is bigger than X. So there we're using the total ordering of, it's actually a partial ordering. We're using, as long as we have a partial ordering relation, that will be valid. Okay, so that's a left rotation. Can you guess what a right rotation might look like? Yeah, it's a symmetric state, right? So Y is going to come up, and Y's right child is going to get orphaned, and is going to get inherited by X on the left side. Okay? We're out of time, but that was actually a really good class. We got through a lot. So on on Monday, I will then illustrate for you how red-black tree insertion is actually done. And then on Tuesday, we'll talk about deletion. And it's complicated enough that you won't be responsible for memorizing how to delete on paper. That's 10 cases. You'll see why. All right. Any questions on this? All right. Well, enjoy the rest of the week. And I'll see you all being well next week.
Are they hearing me? No.